Greetings, this is Mr. T, and this is the video for Chemical Reactions and Conversions, Part 2. In this video, you'll learn about and memorize evidence of chemical reactions, also known as chemical changes, same thing. You'll understand the chemical reactions, and then you'll recognize some patterns. Next, we're going to get into predicting products. So given starting reactants, if we scroll down, here's an example. Given starting reactants, you'll learn how to predict products using the charged balance products rule. Then we're going to get into solution chemistry, where we talk about what a solution is and how we go about labeling it in a chemical reaction, as well as predicting solution-based chemical reactions. So let's go and do the easy stuff. Evidence, and then understanding and recognizing the patterns of basic chemical reactions. Unfortunately, it's really hard to tell if a true chemical reaction occurred unless you look at the atomic level, where you can see actual bond breaking and making. But there are a couple patterns that you can memorize that is evidence of a chemical reaction. It's not 100%, but it's a good start. So here are some nice visually stimulating examples of evidence of chemical reactions. So let's go through these. You have to memorize 4 of them. The first one is a gas is released. So if you see bubbles or you see a floating gas, then that could be a chemical reaction. The next one is the formation of a solid inside a liquid. So you see that yellow solid that formed inside the liquid. That yellow solid we call a precipitate. A precipitate. And anything that's inside water we call aqueous. So in this case, an aqueous reaction with evidence of a precipitate, indicating a chemical reaction. Third one is a color change. Please keep in mind it must be a permanent color change. So here's a color change that occurred starting from the clear one. And then finally, a heat or energy change is observed. So this right here, you can obviously see this is a energy change. That's thermite. It's one of the hottest chemical reactions on the planet. This right here is so hot, it's 2.5 times hotter than lava. It's over 5,000 degrees centigrade. It can actually melt through concrete or melt through an engine block on a car. Pretty hot stuff. You've already learned the expression of energy. If energy is released, we call it exothermic. If it's absorbed, it's endothermic. It means it's going in. So make sure you have those 4 observations memorized. To express in symbols a chemical reaction, we use a chemical equation. So A and B, C and D. The A and B is the reactants. That's what's happening before it's what's happening before a chemical reaction. C and D are the products. This is what's produced after a chemical reaction. So it's produced after a chemical reaction. And then this right here is a reaction arrow indicating a chemical reaction. Make sure you know those terms, reactants and products. Now anything that speeds up a reaction is a catalyst, and usually we'll put the name of the catalyst right above the reaction arrow. It's not actually part of the reactants or products, so it never gets used up. Again, a catalyst simply speeds up a reaction. In the lower right-hand corner, we have physical state symbols. Physical state symbols tell you what physical state they're in. So G for gas, L for liquid, S for solid. AQ means aqueous. That's another fancy way of saying in water. So here are various symbols that accompany a chemical reaction. We just talked about these physical state symbols down below. These right here are catalysts. And then every once in a while we'll have an AND symbol. That's an AND. It's not a plus, like a sodium plus 1. That's an AND. So going back, that AND separates one species from another species. So for example, I could have a reaction where you have magnesium and oxygen. And with that AND symbol, it means two different species. So species 1, species 2. And then it happens to form magnesium oxide. Because it's to the right of the reaction arrow, it's a product. And then if I wanted to, I could put in physical state symbols. So that's solid magnesium, G for gas, and then solid magnesium oxide. Now physical state symbols you really can't reason out. The only way you know what the physical state is to do an actual experiment. That's really the only way to figure out what the physical state is. Our level of chemistry hasn't got to that level where we can automatically figure it out. You can also cheat using what's called a solubility table. The solubility table lists all the previous experimenters' data, and it'll show you what substance is a solid, liquid, or gas. I could give you a paragraph that looks like this, and then I could want you to go ahead and put in the physical state symbols. So aqueous acetic acid, so AQ, is added to solid sodium bicarbonate, yields aqueous, AQ, sodium acetate, liquid water, and then carbon dioxide gas. So make sure you know the relationships between the names and the symbols. Here's another example of a chemical equation. Again, it's the symbols of the chemical reaction. It uses elements. It also uses compounds, and the compounds can be molecules that you learned earlier, molecular formulas, or it could be ionic formulas. So you actually already learned the chemical words from before, and now you're applying those chemical words in a chemical sentence. And we're going to teach you the grammar rules, so to speak. Okay. So these are various classifications you need to be able to recognize. So if I were to show you an equation, like for example this one right here, you would have to let me know what type of reaction pattern it is. In this case, this one right here can be considered a combination reaction. It also has another classification called a combustion reaction. So let's go through patterns so you understand, after you memorize these terms, you understand what to look for. So in a combination reaction, we're combining. Ooh, that's deep. We're combining reactants A and B, and they create the product AB. So two species come together, it's combination. So be able to recognize that pattern. So we're combining. This is magnesium. It's used in flares. It gets really bright, so bright it can burn out your retina. When you set it on fire, it combines with oxygen, forming this white solid called magnesium oxide. decomposition, think of the word decompose. If something is dead and decomposing, it's falling apart. Well, in this case, in a chemical reaction, the reactant falls apart. It breaks apart into two or more products. So here are examples showing this. That's mercury oxide. That's a very, very, very bad poison. It gets in your system, it goes straight to your brain, it loosens up neural connections, and you literally go insane. Good talk. So that's a decomposition reaction. So here are some sample questions. First one is a combination. Next one is a decomposition. Now, a little bit more tricky. What we're going to do is we're going to replace a single element or species within a compound. So in this case, I'm going to go ahead and replace the hydrogen with a zinc, forming a zinc chloride. Replace a copper with a iron, forming iron sulfate. So single replacement. So here's an example of a single replacement. We add in zinc and hydrochloric acid, and the zinc replaces the hydrogen, forming zinc chloride. And then this is combustible hydrogen gas. Double replacement is when we're basically swapping. So here we're going to split apart A and B, split apart C and D, and we're going to swap. So A is going to go with D, and C is going to go with B. Now, a good way to think about this from an ionic compound point of view is that the starting species is always going to be positive, and the ending species is always going to be negative. So when it swaps, the positive goes with the other negative, and then the other positive goes with the other negative. So you need to make sure that you swap them properly, and you need to make sure that it's the positive ion that goes in front. Positive always leads. So silver is going to swap places with sodium, forming silver chloride and sodium nitrate. So other examples. So single replacement, we're simply swapping out one single one. Double replacement, we're swapping out two of them. So be sure to practice those. Here are four we just covered. The fifth one is a combustion reaction. Basically, it's in a reaction that involves a gas. So let me go ahead and use my purple highlighter. So if you see a gas present, O2 gas, other types of gases like S2 gas, N2 gas, you had to memorize the homodiatomic molecules, fluorine, chlorine, bromine, iodine. That whole ice cold beer mnemonic trick. Make sure you have those down. Have no fear. Ice cold beer. Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine. So if you have a gas present, then it's a combustion. Can you have more than one classifications? Yes, you can. So let's see. This one right here is both a combination reaction and it's a combustion reaction. Excellent. Now we're going to get into predicting chemical products through balancing charges, also known as charge balancing. So we've finished with this part. We also introduced subscripts for physical state symbols. And now we're going to get into predicting products through charge balancing techniques. So these are the problems that we're going to be working with. And I will give you a walkthrough through each of these problems to demonstrate writing a complete equation using the charge balancing techniques. Going back to revised slide 24, we want to determine the ion form of each element or polyatomic ion in a substance. For example, magnesium plus oxygen, turn them into ions. So magnesium is going to be a 2+. That's according to the periodic table because magnesium is a representative element in group 2. Oxygen is going to be a 2-. Again, looking at the periodic table, it's in group 6. So 6 minus 8 is a -2. We then need to figure out whether the reaction is a combination reaction or a double replacement reaction. So if it's a combination reaction, then we're going to add the ions together using the charge balancing technique we learned before. So in this case, our answer is going to be magnesium oxide, because we just needed one of the magnesium and one of the oxides in order to create the magnesium oxide. So just as in the previous segment where we talked about forming our ionic formula from the starting ions, we're going to do the exact same thing here. Pretty straightforward. The next one, aluminum plus sulfur dioxide, is also a combination reaction. So again, turn it into a single ion. Aluminum 3+, and sulfur. Aluminum is in group 3, sulfur is in group 6, so that's a 2-. So here we have single ions. Now, notice that word single I keep using. Technically, because of the subscript 2 right there, that means there's 2 of the ions. However, we're only going to focus on one ion. So you need to go ahead and figure out the charge balance rules in this one. In this case, we're going to need the least common multiple. The least common multiple in this case is going to be 6. Because for aluminum, it's in multiples of 3, so 3, 6, 9. Sulfur is in multiples of 2, so 2, 4, 6. So the least common multiple between the two is going to be 6. So I'm going to need 2 of the aluminums, and I'm going to need 3 of these sulfides, and it's going to create Al2S3. Now, I temporarily created extra ions just so that we can create a charge balance product. It has nothing to do with that starting 2 in the sulfur gas that you see up there, the S2. Now we're going to go to the next one. Magnesium fluoride and calcium chloride. So you'll notice that there is 2 ion species and 2 ion species. So in this case, it's going to be a double replacement reaction. So that means you're going to have to swap ions. So the first thing we do is we go ahead and create our magnesium 2+, and then we figure out the ion for a single one, not both of them, fluoride with a minus. Here we have chloride, and drawing upon the previous chapter's work, you have to figure out what the charge is on that ion. So the total positive and negative should equal 0, and there's one of each. If there's one negative, then you're going to need one positive, so it should be copper plus. Now we're going to need to go ahead and swap them. So the positive goes with a negative. So this positive, oops. Excuse me. So this positive magnesium 2 plus is going to go with the negative magnesium chloride. And then the positive chloride is going to go with the negative fluoride. So many books just go ahead and write it like this, where they rearrange them. So there's a magnesium with a 2 plus, chloride minus, copper with a plus, fluoride with a minus. And it's going to be magnesium chloride, MgCl2, and copper fluoride. So then we go ahead and we arrange it up here. And it doesn't matter which ionic formula you write first. So it'd be magnesium chloride here, for example, copper fluoride for the other one. Now, another way of doing it to help speed you up is to just simply write the broken up magnesium and then fluoride here, copper chloride here, and then you just kind of circle across. So copper fluoride, magnesium chloride. All right, let's go ahead and do the next one. These are polyatomic ions. It just so happened that in the previous ones, I broke it up by ions, but you could have broken up by atoms, which is always a possibility. But we're just going to stick with ions for this class, and we're going to do the exact same thing with polyatomic ions. So we break it up where it's a sodium with a positive charge, just one of them, not both of them. And then a carbonate, this is one that you had to have memorized, with a 2 minus charge. Then there's a hydrogen with a positive charge and a sulfate with a 2 minus charge. So I'm just going to write it like this. And then I'm going to swap them by me circling them. And then it's going to be H2CO3, also known as carbonic acid, and this is going to be Na2SO3, known as sodium sulfite. Again, it doesn't matter which one we write, which ionic formula we write first. You can write Na2SO3 plus H2CO3. Now, we are just sticking with combination and double replacement reactions. That's all I'm going to test you on. You could have such as in the lab, you could have more complicated ones, although those won't be on the quiz or exams. For example, you could have a decomposition reaction where you'll have a side reaction such as carbonic acid, the H2CO3, decomposing into water and carbon dioxide. So then your final answer in a decomposition reaction would look something like this. You'd actually have 3 products. Now again, I'm not going to do that to you. I'm just going to want you to do a simple double replacement reaction, and that's it. So it looks like this right here. Alright, let's keep on going. This is iron. This is chloride. Because there were 3 chlorides, then the iron has to be a 3 positive. Because 3 positives and 3 of the negatives equals 0. Here's the ammonia with a positive charge. Here's the nitrate with a negative charge. Please notice that you have to have these memorized. So let's go ahead and write them again. And then again, you're going to go ahead and circle them to swap them. That's going to give you ammonium chloride, NH4Cl, and is going to give you iron nitrate. And then you have to write it up here. NH4Cl plus FeNO3, ammonium chloride and iron nitrate. Let's do the last one. This is silver. Although it's a transition metal, there's only one type of charge, so it's Ag plus or silver plus, anion. And then here we have gold. Gold can either be a +1 or a +3. Because there's one of the negatives, a total of 1 negative, we need a total of 1 positive. And so since there's only one of those gold, then it has to be a positive. I then go ahead and rewrite it. So I have the ionic formulas separated out into individual ions, and then I circle to swap. So then this is going to be gold cyanide, and then this will be silver nitrate. And so up here you could write gold cyanide and silver nitrate. Alright, so let's go back to our slides. I do want to point out, we're going to go ahead and talk about in a separate part how to add physical state symbols. Well, actually, we already did talk about physical state symbols. You need a solubility table in order to add them in, or you need to do it by experiment. But the other thing you need to do is equation balance. In equation balancing, taking a look at slide 23, we need to make sure that the number of reactant atoms equal the number of product atoms. So for example, on the left-hand side, we have 1 carbon. On the right-hand side, we have 1 carbon. So the number of carbon atoms on the reactant and product side are balanced out. And the number of oxygen, so there's 2 oxygen, those are balanced out. If you take a look at magnesium, there's only 1 magnesium and 1 magnesium, so they're balanced out. Take a look at oxygen, there's 2 oxygen, and then there's 1 oxygen. Because these are not balanced out, we have to do extra steps by adding in something called coefficients. Now, in this particular Part 2 commentary, we do not get into that yet. So you'll notice the fine print where it says equation balancing with coefficients is not required for these examples. Don't worry, we'll get into that in Part 3. Just wanted to give you a heads up if you're trying to figure out how come the number of atoms on the reactant and product side don't equal each other. All right, so let's move on. Now we're going to get into solutions. We have some simple definitions. 2 of them are here. Another one is missing. The first one is solute. The next one is solvent. And then there's a third one that you have to write down called solution. A solution is the sum of the solute and solvent. Now, simple definitions. Solute is found in a mixture. The mixture can be homogeneous, where you see one thing, or heterogeneous, where you see 2 or more things. So in a heterogeneous mixture, the lesser amount is considered the solute. The greater amount is considered the solvent. And then, again, solution is the sum of solute and solvent added together. So in the example right here, it looks like there's a lot more water than there is salt. So water is the solvent, and then salt is the solute, and then together that's a solution. In this example right here, looks like there's a lot more water, so copper sulfate is the solute, water is the solvent, and then added together it's a solution. Now, for many substances, solutes like to spread out evenly, and that's a hallmark characteristic of a homogeneous solution. So on the left piece of volumetric glassware, that's before, and then on the right side it's after, and then you can see it's all spread out. And that's because the individual particles that make up the solute, they like to spread out. Now, many people start to think that it must be the solute particles that try to spread out. Actually, what makes it spread out isn't the solute particles. What makes it spread out is the water. The water actually picks off the solute particles and then surrounds them, suspending them in what's called a solvent cage. So here are the water molecules right here. The water molecules achieve this due to opposite charge attraction. You already learned that water is polar, and the oxygen is partial negative, and the hydrogen side is partial positive. Well, the partial negative of water, for example, may be attracted to the positive sodium for sodium chloride, for example. Opposite charges attract. And the water molecules, for example, will surround the sodium in what's called a solvent cage. Here is another example. for chloride, where the partial positive on the hydrogens are attracted to the negative on the chloride. And then again, opposite charges attract. Now, it doesn't need to be a complete ion for water molecules to dissolve a substance. They can be molecular compounds. Here's a nice pretty example of what I just showed you. So the partial negative is attracted to the positive on the sodium, and it surrounds it in what's called a solvent cage. So when it does that repeatedly for each one of the particles in the substance, then we say that it's dissolving. Because the substance is surrounded in solvent cages and it floats around in water, we say it goes from being solid, S, to being dissolved in water, or aqueous. Now, a lot of people think that this is a chemical reaction. This actually isn't. This is a physical change. Why? Because this is not permanent. The minute you take out the water, you dry it out, then this sodium and chloride will immediately go back to its original solid form. Whereas in a true chemical change, it's permanent and it wouldn't go back. So now we're going to go ahead and show you a quick video. So in this video, we have some salt and water, and the salt's going to be put into water. There's the salt made up of sodium and chlorides. Then we're going to have water come along as the salt dissolves in water. We have water come along, and the partial positive on the hydrogens are attracted to the negative on the chloride, and it picks off the particles that make up salt, kind of like ants, leafcutter ants, cutting apart pieces of a leaf to take it back home. Again, we call the suspended sodium and chloride solid. Excuse me. We call the suspended sodium and chloride surrounded by water molecules solvent cages. So this happens over and over and over until the salt is completely disassembled and separated. Now we're going to be looking at two solutions of salts, and we're going to be mixing them together. So let's go through this terminology right here. So here I have one test tube, and the test tube, for example, might contain something like lead nitrate. Now this is dissolved in water, so we say that it's aqueous. And then we may have another dissolved solution of potassium iodide. And again, it's aqueous because all the potassium iodide is dissolved in water. What we're going to go ahead and do is stick both of them inside a beaker. And then you're going to have a combination of dissolved lead nitrate and dissolved potassium iodide that's inside. Now this is a straightforward double replacement reaction. Whoops. It's a PbNO3 and then 2. My bad. Uh, but again, this is going to be a straightforward double replacement reaction. And learning the rules that we just taught you, we're going to have a double replacement product of lead iodide, and we're going to have potassium nitrate. And again, all of this occurs inside water, so it's all in solution. Now let's go ahead and investigate the physical state symbols. So the lead nitrate originally was completely dissolved, so it's aqueous, AQ. Just as we saw over here, AQ. The original potassium iodide was AQ, aqueous, so AQ, aqueous, and I'm oscillating between little a and capital A. That's okay. However, as soon as we made a double replacement product, only the potassium nitrate remains dissolved inside water. So even though it performed a product, water still tears it apart into its individual potassium and nitrate ions. Lead iodide, however, stays solid. So the water actually cannot break it up into ions. And it actually creates a really pretty color. It creates a nice, solid, what we call a precipitate, because the solid is formed in water. So it creates a nice precipitate. It starts floating for a bit, and then eventually it'll start collecting on the bottom of the beaker, for example, over time. So let's see another example of the same thing. So in this video, on the very left side, we see solid potassium iodide. If we follow my my cursor, that Erlenmeyer flask contains dissolved potassium iodide in water. And then on the right-hand side, we have lead nitrate, and it's solid lead nitrate. And then in the Erlenmeyer flask where my cursor is, that's dissolved lead nitrate. Now that means that all of the lead nitrate ions are in a solvent cage and they're floating around, and it's aqueous. Same thing goes with potassium iodide. Now when we stick them together, then we're going to create two new products, and one of them is going to be a permanently solid. It doesn't dissolve. So let's go ahead and see those two Erlenmeyer flasks, those are the glasses on the left and the right, be combined into a beaker. There we go, and boom. So there's a lot of precipitate there. Initially the precipitate's floating, and then eventually it'll start to settle on the bottom. So here's a computer animation where on the left side we see lead nitrate, and on the right side we see potassium iodide. You'll see a lot of words in there. This is taken from a student who made this computer animation. So that's his. Those are some of the works in his native language. So lead nitrate, potassium iodide, they're in these two beakers. Now we're going to go ahead and put them together. Again, notice the individual ionic compounds that you see in the circle. And let's continue. We put the beakers together. And using our special molecular scope that all professors have. It's a secret, don't tell anybody. We can zoom in and see the formation of the double replacement products. So the iodide goes near the lead, and it forms lead iodide, And one of its properties is it likes to be a precipitate in water. Likes to form a solid in water. And the rest of them are free-floating potassium nitrate, where water does dissolve it into a solvent cage for each of those, and they continue to be aqueous. So after those two videos, then this statement should make sense, where if we have two solutions, like for example, one solution in each beaker containing the salts, such as the lead nitrate and potassium iodide, and then we mix them together, they will perform a double replacement reaction. So if we go to the next slide, slide 30, this would be an example: silver nitrate, ammonium chloride. This is before we mix them together. They're dissolved in water. They're aqueous, so AQ. And then afterwards, a double replacement reaction occurs, and one of them may form a solid. Now let's go ahead and go back. So in general, the products may stay as a aqueous substance, and because they're in individual solvent cages floating around, we call those spectator ions because they don't really do anything. Compare those to the other group that forms a solid. Those ions actually came together and formed a solid, which we call participating ions, because they participated in creating a solid. And another word for solid is precipitate. Also another word for solid is insoluble salts, but I like precipitate the best. Now those results, which will summarize spectator ions as aqueous, and participating ions we will summarize as a precipitate, which is a S for solid. Those are going to be recorded in the final equation. The final equation for a solubility reaction is going to be called, jumping around, it's going to be called a molecular equation. So let me just go ahead and erase this really quick. So whenever you're dealing with a solubility reaction where you're mixing together two aqueous reactants and you're forming a product, the equation that that's generated is called a molecular equation. A molecular equation. I'm going to test you on molecular equations because they look and they function just like the double replacement reactions that we've been studying all this time. So I could give you the starting reactants here and then ask you to do a double replacement reaction. And those are the double replacement products. I will then give you a paragraph that's highlighted in yellow. And based on this data, you should be able to fill in the physical state symbols. So the starting reactants were dissolved in water completely, and it was aqueous. One of the final products, silver chloride, became precipitate, so we have to put S for solid. And usually we underlined it. And then the other one, since it's not mentioned it's a solid, then it stays aqueous. So only the silver chloride had participating ions. The ammonium nitrate, because it stated aqueous, those are spectator ions. So here's another one. Potassium hydroxide, sodium chloride. There's our starting species for each. It's aqueous, it's dissolved in water, so realistically they're in ion form. And then both of them, even though they form new products, they stay dissolved in their solvent cages. So you can consider both of those as being spectators because they don't do anything, they just kind of float around. So in summary, if I give you the starting reactant and I give you a paragraph that looks like this, you should be able to predict the products as well as put in the physical state symbols for these type of molecular equations.